Okay, so if you would write down f of x equals 4 divided by x minus 5. So very similar to the problem that we just had. X minus 5 is in fact just a shift to the right 5, so the vertical asymptote, so it still occurs. It still has the same basic shape, but now we have this 4. So what I just think of that is 4 times 1 over x minus 5, and if you see it like that, then you can see that that's a vertical stretch by a factor of 4. So if I were to think about the values, right, so we're going to go to the right 5, so I'm going to draw an x and a y. And you don't necessarily have to sketch this, you can just say where the vertical asymptote occurs and what the domain is, okay? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 1, 2, 3. Okay. So I know that the vertical asymptote occurs when the denominator equals 0, so that's at 5, so x equals 5. 1, 2, 3, 4, 5. So I'm going to draw a dotted vertical line. And I know that that means my domain is all real numbers except 5. So what I want to do is I want to explore this size. Like what does that 4 do? We should know it's just a vertical stretch, but let's just see what it looks like. So if I were to plug in, if it's a vertical stretch, I probably need to go higher. 7, 8, yeah. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So if I plug in, let's go with 6. 4 over 6 minus 5, so that's 4. So at 6, I'm at 1, 2, 3, 4. At 7, I'm at 4 divided by 2, so that's 2. And at 8, I am at 4 thirds, so 1 and 1 third. And then let's say at 5 and a half, right? So 4 divided by 5 and a half, sorry, 5 and a half minus 5, so that's a half. Divided by a half is the same thing as multiplying by 2, and that's 8. So I would be way up here at 8. And so you can see how it just kind of stretches it out vertically by a factor of 4. And then the same would go on this side. If I were to plug in 4, I would get 4 divided by negative 1, so that would be negative 4. 1, 2, 3, 4. And then if I were to plug in 3, I would get 4 divided by negative 2, so negative 2. And then I would get negative 2, so, or 2, so 4 divided by negative 3, so negative 4 thirds. So it would follow the same pattern. Basically, well, that should be, okay. If x equals 0, I get negative 4 fifths. I didn't want to sketch that. Like, if I'm going to cross an axis, I better, like, know where it is. So when x equals 0, I get negative 4 fifths, so negative 0.8, so somewhere in there. So I would know it would look like this. And then at negative, or at positive 4.5, it would be at negative 8. So, there we go. Okay, it did say to describe, use limits to describe the behavior at values of x not in its domain. So let's talk about it. As x approaches the vertical asymptote 5, from the right, yeah, of f of x, the function is approaching positive infinity. Whereas over here, the limit as x approaches 5 from the left. So as I approach 5 from the left, the function is going down to negative infinity. And we see that again, or we see that in that image right there. Okay, let's talk about this one. So the main difference is this negative out front, and if we recall what we learned about transformations, a negative outside the function is a reflection across the x-axis. A reflection across the y-axis would be like a negative 3x plus 8. Then you'd have a reflection across the y. Although remember that with a odd function, a reflection over the x and a reflection over the y, I mean if it's exactly centered at 0, 0. If I reflect this, what am I trying to say? Oh, yeah, if I reflect this over the y-axis, it would look like this, right? But if I reflected the original over the x-axis, I would still end up with the same thing. So they are, in effect, the same. All right, let's explore for a second. As far as the value not in its domain, well, the denominator cannot equal 0, right? So when the denominator equals 0, x equals negative 8/3, that I must have a discontinuity. I can't be continuous where I don't exist. And in fact, we have a discontinuity at x equals negative 8/3, and it is a vertical asymptote. Okay? If I were to think about the graph of it, though, so negative 8/3 is negative 2 and 2/3. So negative 1, 2, 3, 4, 5. 1, 2, 3, 1, 2, 3. Okay. So I know vertical asymptote at negative 2 and 2/3. So somewhere in here, I don't know if that's lined up, but kind of weird. Oh well. Let's plug in some numbers and let's see what's happening, okay? Intelligence says that if this is what it normally looks like and we flip it over, then this should be up here and this should be down there, right? So let's prove it. If I were to plug in negative 2, so if I plug in negative 2, then I would get negative 1 over negative 2 times 3 is negative 6, and negative 6 plus 8 is 2, or positive 2, so negative 1 divided by 2 is negative 1/2. So at negative 2, I would be at negative 1/2. At negative 1, I would be at negative 1 over negative 3 plus 8. That is 5, so negative 1/5, negative 0.2. Sorry, I'm thinking for a second. Plug in negative 1/5. I'm confusing myself for a second. If I plug in negative 2, I get negative 1 divided by... Oh, duh. Oh my gosh. Wow. Okay. I hadn't rotated in my brain, so I thought something is wrong. Okay, negative 1/5 is negative 0.2. And then if I plug in 0, so if I plug in 0, that basically just goes away and I get negative 1/8. So that's like right here. And let's go ahead and plug in 1. If I plug in 1, I would get negative 1 over 3 plus 8, so 11. And the denominator, as I plug in 2, 3, 4, 5, 6, 7, 8, 9, the denominator is just going to get larger and larger and larger. It's still a negative number, though, because it's negative 1 divided by. It's just getting closer and closer to 0 from the negative side. So, in fact, we do have that horizontal asymptote, just like I said, and it flips. And then there we go. So we would do something like this. Okay? And there we go. So we could go ahead and say that the limit as x approaches negative 8/3 from the right-hand side, so from the right-hand side, is going down to negative infinity. Without an f of x, or without the actual function there, it doesn't make sense. So please don't just write the limit without the f of x equals negative infinity, because that you could also write the limit as x approaches negative 8/3 from the right of negative 1 over 3x plus 8 equals negative infinity, but you cannot just write it with the limit equals. Okay, that doesn't make sense. That's like saying the square root equals 7. Doesn't make sense. Okay, from the right-hand side, or from the left-hand side, if we were to plug in negative 3. So if I were to plug in negative 3 right here, negative 3 times 3 is negative 9. Negative 9 plus 8 is negative 1. Negative 1 divided by negative 1 is positive 1. And if I were to plug in negative 4, negative 4 times 3 is negative 12. Negative 12 plus 8 is negative 4. Negative 1 divided by negative 4 is positive 1/4. So it'd be somewhere in here. So it's doing the same thing, just on the opposite side. Oop, I missed. Approaching 0 and then approaching infinity. So we would say the limit as x approaches negative 8/3 from the left, so approaching it from the left-hand side, from the negative side of f of x equals positive infinity, because it's going up. Okay, and you can see how it is evidenced there. Let's do one more before I do another one. Okay, Vertical asymptotes versus holes in the graph. So this is kind of interesting. If I think about 3 over x, it is the basic 1 over x function just shifted, or not shifted, just vertically stretched by a factor of 3. So 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. If I were to plug in, say, 1, I would get 3. 2, I would get 3 halves, so 1 and a half. 3, I would get 1, and then it would just keep getting smaller. 3 divided by an increasingly large number is just getting smaller and smaller and smaller. So it would do this. And then if I divide by an increasingly small number, I get closer and closer to 0. It's going to go to infinity. So 3 divided by 1/10, I don't like that, would be 3 times 10 over 1, so that's 30. So uh, gets really large pretty quickly, and so we have the vertical asymptote at x equals 0, and then we have a horizontal asymptote at y equals 0. And the same thing on this side, just vertically stretched. If I plugged in -1, we get -3, -1.5, -1, and then there we go. So we have a vertical asymptote at x equals 0 because the denominator equals 0, and because of that factor being only in the denominator, the values are constantly changing. All right. Over here, however, we have x in both the numerator and denominator, which is kind of interesting. So let's explore what happens there. Now you might be saying, can't I just simplify those out? And the answer is kind of. So yes, x is a factor in the numerator and denominator, but when you simplify it out, it's not like it was never there. It was there in the original, and so it has to be accounted for. So what happens is you get a graph like this. If I were to plug in 1, then I would get 3 times 1 divided by 1, so that's 3. If I were to plug in 2, I would get 3 times 2 divided by 2. 3 times 2 and then divided by 2 is still 3. If I were to plug in 3, I would get 3. If I were to plug in any number, I would get 3. If I were to plug in -2, 3 times -2 divided by -2 is 3. I would get 3 for all of these numbers except when the denominator equals 0. So the denominator equals 0 is 0, but in fact, because it's in both the numerator and denominator, they don't affect anything but the value when they equal 0, which is why we have just a hole in the graph at x equals 0. Now I drew the hole kind of large so that we could see that it's an open hole in the graph, but it is infinitesimally small, because at 0.001, right, 1/1000th, divided by 0.001. So at 1/1000th, really close to 0, it's still 3, right? It is 3 for every single moment except at x equals 0, where both the numerator and denominator. So if the factor is in both numerator and denominator, and this is going to be important. I'm putting it in parentheses. It's not like it's going to show up a whole lot, but it's important that you don't just memorize this as a rule whenever it's not actually true. The factor is in both the numerator and denominator an equal number of times. Let's add if a factor is in both numerator and denominator, then the function has a hole at the 0 of the factor. Okay? So if a factor is in both the numerator and the denominator an equal number of times, then the function has a hole at the 0 of the factor. Okay? The 0 of this factor is 0. It's kind of hard to see it as a factor, so let me draw you another example. What if I had 3 times x plus 2 divided by x plus 2? The 0 of x plus 2 is -2, because -2 plus 2 is 0. So this function will look exactly the same thing as this one, only the hole would be at -2, comma 3. not at 0, comma 3. So it's interesting because the hole in the graph has an actual coordinate point. It's a location. This one right here, a vertical asymptote, that's a complete huge discontinuity. I mean, we've got two different discontinuities. This is called an infinite discontinuity. Vertical asymptotes are. And this is called a removable discontinuity. And the reason why this is called a removable discontinuity is because you could redefine the function to exist there. You would just fill it in, say, hey, let it be this function, except at 0, let it be 3. And I think of it as like a boat. If you're in a boat in the ocean and you spring a tiny leak, what can you fix it? And I'm like, yeah, you can plug the hole. And so you've removed the discontinuity. You've removed the hole in the graph. And so if you wanted like a definition for this for vertical asymptote, I would say if a factor is in the denominator and only the denominator, or if the factor is in the denominator more times than the numerator. That's where it gets kind of annoying. I would just say if the denominator and only the denominator equals 0. But then again, that doesn't. The equal number of times, because you have me as a teacher, I want to make sure that we talk about all the various options. So like, if you had 3x plus 2, 3 times x plus 2 to the third divided by x plus 2 to the third, still hole in the graph because of the same amount. But if you had 3 times x plus 2 divided by x plus 2 squared, well, you simplify one of those out, you're still left with an x plus 2 in the denominator. A vertical asymptote is more powerful than a hole in a graph, straight up. So that would mean the vertical asymptote would trump the x plus 2, the common factor, and say, no, you don't have a hole in the graph, you just have a vertical asymptote. So that's what I mean by if it's just the denominator. So once you get rid of the common factors, you can just say, now only the denominator equals 0, therefore vertical asymptote. Okay, I'm going to end the video and pick back up with holes versus vertical asymptotes in a second.